I'm sorry. We are late today. Тут спрашиваете, в порядке с ссылкой? Okay, so there was a problem. I don't know precisely what kind of the problem, but so we start 15 minutes later. Okay, I'll try to compensate a little bit, so we'll proceed without break, and maybe 5 minutes later I'll take 5 minutes. Okay, so today we start next lecture, chapter 4, limits, next chapter, limits and continuity. Section, okay, we enumerate sections according to lectures. So what means yes here? Is there something wrong with the link? So something wrong with the link, right? I hope now no problem. Okay. So today I think lecture 12, so section 12.1, limits of functions. We'll use several abbreviations, several notations. So B from bow of P delta is by definition the following interval. So for delta positive, P a real number. So we have an interval around a point P. That is a neighborhood, right? Neighborhood. Neighborhood. And also I would like to recall what means yeah, maybe okay, limit point. What is limit point? Limit point of a set, let's say D. What it means, limit point, it means, so a limit point of a set D means a point such, a point P such that the intersection B of P D without the point P with our set D is not empty for arbitrary D greater than 0. So look, what is What is it? So let me indicate the set D somehow like that, right? Maybe this one, and that is the set D, right? And what is limit point? Look, for example, that one, that is P, right? What means limit point? Doesn't matter how small is the interval B of P delta, so that is P plus delta. Analogously, here we have P minus delta. So it doesn't matter how small is this interval. For arbitrary delta greater than 0, there are points inside that interval of our set D different from the point P itself. Why we should exclude P? Because, for example, look at that point. Here, if I'll choose very small interval like that, the intersection of that interval with our set D contains the unique point P. So that is why we exclude that point P. So, in other words, here the point is isolated. I don't want to give a formal definition of an isolated point just now. We are talking about limit points for a while, nothing else. Okay, now I can give the formal definition. Let P is a limit point of the set D maybe it's better here also to use another article of the set D. Then, okay, what is the limit? The value of limit, which let we use capital L. Let P be, sorry, I'm very sorry. Let P be a limit point of the set D. L is the limit of the function L is the limit of the function f from D to R at P, and that is denoted by limit as x tends to P f of x equals to L if for any epsilon greater than 0 there exists delta greater than 0 such that for all x in D modulo x 0 less than modulo x minus delta x minus p less than delta, the inequality modulo f of x minus L less than epsilon holds. Or in quantifiers, for arbitrary epsilon greater 0, there exists delta greater than 0, such that for all x in D 0 less x minus p less than delta, modulo f of x minus L less than epsilon. That is the definition. Also, it is called epsilon delta definition or Cauchy definition. Cauchy definition. And of course, to understand it better, we need to consider several examples. So, example 1. So f from R to R is given by f of x equals to 5x minus 7. So we want to prove that the limit is equal to 3. So how to proceed? Just by definition, right? So as we did for the limits of sequences, we start with the very end. Look at the last inequality. We want to find when this inequality is valid. Let's substitute. So substitute 5x minus 7 minus 3 less than epsilon. Or what is it? That is 5x minus 10 less than epsilon. Or 5 times modulo x minus 2 less than epsilon. Or x minus 2 less than epsilon over 5. All those inequalities are equivalent to each other. That is a chain of equivalent inequalities. Now, look at the rest. So what we want. Here D is the set of all real numbers. Hence, definitely every point of the real line is a limit point. So we can find points of the real line as close to, let's say, 2 as we want. So what we want for arbitrary epsilon greater than 0, we need to indicate delta greater than 0 such that for all x in D, it means in R, we can omit it with the following supposition. this inequality should be satisfied. Now look, this inequality is equivalent to the very last, so it will be satisfied automatically if we'll put delta equals to epsilon over 5. Why? Because now look, given arbitrary epsilon greater than 0, right? So, given arbitrary epsilon greater than 0, there exists positive number epsilon over 5, we denote it by delta, there exists this delta. Now, once 0 less than modulo x minus 2 less than epsilon over 5, once we have this inequality, then automatically we have this and that inequality as well. So we are done. And maybe small modification to explain how it works. So in fact, what we did, we just, how we could compute these three, we just substitute 2 and find the limit, right? That is naive point of view. So if you don't know anything about limits, you just substitute, that's it. Now let's modify a little bit. So f now from R without 2 to R, and the function will be defined like that. Now the function is not defined at the point 2 because we have 0 in denominator. But how we can compute the limit? And that is why this epsilon delta language appeared, in fact. So the idea is like that. Look, why this is true? Because when we are talking about the limit, we exclude the point x equals to 2 itself. So you see, everywhere in the definition there is the inequality modulus greater 0. Modulus is greater 0 means that the expression under modulo cannot be 0. So it means x minus p is not equal to 0. X doesn't equal to p. So it means when we want to compute the limit as x tends to 2, then we can exclude x equals to 2. And if x is not equal to 2, then x minus 2 is not 0, hence we can cancel this expression. And that is why this first equality is valid. Then the second equality was checked before. But now look, it's a very strange story. So firstly, we suppose x is not equal to 2. Firstly, right? If x is not equal to 2, then we can cancel. After that, we substitute x equals to 2 and compute the limit. That is, it seems rather strange, but to explain it, this formalism is necessary. So, why we can firstly suppose that x doesn't equal to 2 and then to substitute x equals to 2? Why? It seems not logical, but the logic is as follows. So, we exclude the point P itself. We exclude it, but we are interested in the values of x which are as close to P as we want. So they are very close to P. Arbitrary x which is close to P is considered. And that is how it works. So, in fact, here, when we compute the limit, we are looking at the values of x which are as close to 2 as we want. So, very, very the difference between x and 2 is very, very small. Yeah. Okay. More example. Okay. And there is a figure also. So, example 2. Example 2, f from semi-interval 0, 1 to r is given by f of x equals to x squared plus x. So p equals to 1, l equals to 2. We want to prove this limit for such values of p and l. So let me write down what we want to prove. For arbitrary epsilon greater than 0, there exists delta greater than 0 such that for all x in 0, 1 such that 0 less than x minus 1 less than delta, we should obtain this estimate. That is, so here capital L, here P. And that is our function f, and here g. Okay, let me write down what mean those two inequalities together. So the second inequality, the second, is equivalent to couple of two inequalities. Either 0 less x minus 1 less than delta, or minus delta less x minus 1 less than 0. So we exclude x minus 1 equals to 0, then this couple of inequalities can be rewritten as either x greater than 1 and less than 1 plus delta, or 1 minus delta less than x less than 1. So this inequality, double inequality with modulus, is equivalent to couple of two double inequalities. But x belongs to semi-interval. It means the first inequality is impossible. Hence, we can rewrite this quantifier as follows. For arbitrary epsilon greater than 0, there exists delta greater than 0, such that for all x 1 minus delta less than x less than 1, we have the inequality modulo x squared plus x minus 2 less than epsilon. Now, look at this quadratic expression. We can rewrite it as, what is it? That is x minus 1 times x plus 2, right? So, our inequality, last inequality which we want to check, is equivalent to, say, x minus 1 times x plus 2 less than epsilon. That is what we want to check. Now, x minus 1 we know is less than delta. And what is about x plus 2? Look at x plus 2. Under those suppositions, we have less than 3 and greater than 3 minus delta. So, if we substitute, look at here, if we substitute our bound for x plus 2 into this inequality, then it suggests that we can choose delta equals to epsilon over 3. Of course, it doesn't guarantee that 3 minus delta is not very large. So, in modulus, in principle, yeah, if delta is extremely large, for very large epsilon, delta may be very large, so 1 minus delta may be very large in absolute value. And then, of course, x plus 2 can be very large in negative. And that's not very good. But what we can do? We can say, for example, delta equals to minimum of epsilon over 3 and let's say 1. Then that is a positive number, right? And then what we obtain? For arbitrary x, if this inequality holds, then, for example, delta is less or equal to 1, right? Then 1 minus delta is positive, since delta less or equal to 1. Less or equal than, yeah, greater or equal than 0, right? So it follows from this double inequality x is greater than 0, hence x plus 2 greater than 2, right? So from the inequality x plus 2 is between 3 minus delta and x plus 2, it follows that modulo x plus 2 less than 3, because x plus 2 greater than 2. Then we can deduce from this inequality that this product is less than 3 times modulo x minus 1, and again x greater, yeah, it's okay. 3 times modulo x minus 1 and 3 times modulo x minus 1. X minus 1 is less than delta in modulus, and delta less or equal than epsilon over 3. So less than 3 times epsilon over 3, and that is epsilon. So once again, for arbitrary epsilon greater than 0, we found positive delta from that definition, such that for all x satisfying the inequality 1 minus delta less than x less than 1, we can deduce two facts. The first one, x is greater than 0, hence x plus 2 greater than 2, and since x plus 2 is between those two values, we obtain modulo of x plus 2 less than 3. Then we can estimate product of those two modulus by 3 times modulo x minus 1, and then we deduce the second thing from this double inequality. So x is greater than 1 minus delta less than 1. It implies that double inequality, and we are interested in the right hand side, so x minus 1 less than delta, which is less than epsilon over 3, less or equal. So we can substitute here 3 times epsilon over 3, and that is epsilon. Yeah, once again, why delta is minimum. So delta should be simultaneously less than 1, because if delta less than 1, then 1 minus delta greater or equal to 0, and we guarantee that x plus 2 cannot be negative, right? So x plus 2 from that inequality, x plus 2, we know x plus 2 is non-negative. In fact, it's greater than 2. But the main point is non-negative. So x plus 2 less than 3, hence modulo of x plus 2 is less than 3 as well. So we want to estimate this product. Somehow we have to estimate modulo x plus 2. And that is how. Okay. Yeah. hope I answered. So we want to estimate simultaneously both values, x minus 1 and x plus 2, using just this estimate for x. So delta less than 1 guarantees x is positive, hence model of x plus 2 less than 3 from the right hand side. Yeah, okay. Okay, now geometrically, what means geometrically this definition of the limit? Okay. So we have a graph of a function y equals to f of x. We have a point P. In fact, we don't care about the value of our function at the point P. So it might happen that the graph has a break just at the point, right? So the point can be excluded. So it may happen that the value of the function is here. So that is f of p. Doesn't matter. Absolutely doesn't matter. The value at the point is not important when we want to compute the limit. But values of the function as close to p as we want are very important. That's it. So look, that is the limit, right? That is the limit. So we can choose arbitrary small, that is L plus epsilon, L minus epsilon, arbitrary small neighborhood of the limit here, right? Then we can guarantee the existence. Look. So, for example, here, p plus delta, p minus delta. So we can find a neighborhood of the point P such that once we take arbitrary x in this neighborhood, except for the point P itself. So look at the value of the function, and this value is in the given neighborhood of L. So given arbitrary small neighborhood here, you can find a neighborhood of P which is mapped inside the epsilon neighborhood of the limit. That is the geometric definition of the limit. And we don't care about the value of the function at the point P itself, only very close to the point. But not, yeah, we don't care about the values at the point P. And okay, yeah. Yeah, and indeed, what I did, I considered slightly different thing. Yeah, what I did, in fact, was good for this minus infinity, and here minus infinity. Yeah. Of course, yeah, because Otherwise, I don't care about this inequality. Yeah, I forget about this definition. Yeah. Otherwise, it was without any sense, this. Yeah. So this inequality guarantees x greater than 0. Yeah. Okay. Okay. So now the other definition of the limit. So the first was Cauchy definition. Now I'll give it as a theorem now. Theorem 1, and the title. Firstly I need to give a definition, right? No, I don't want to give the definition. So, theorem 1, sequential characterization of the limit. Let P be a limit point of D, F be from D to R. L is the limit of F as P as X tends to P if and only if for arbitrary sequence xn in D such that xn not equals to P and 1, 2 and so on, and the limit xn equals to P, there exists the limit of the sequence of the values, and it is equal to equals to L. And that is called also this this is called Heine definition. Heine definition. So proof. proof. Okay, so we start from Cauchy-Heine. So we suppose that the Cauchy definition is satisfied, and we have to prove that the Heine definition is satisfied as well, right? So take a sequence xn in D, xn not equals to p, and the limit equals to p. Then, from the definition of the limit of a sequence, right, we can find a number n natural such that for all n greater than this natural n, modulo of xn minus p is as small as we want. And look, I didn't write here for arbitrary epsilon greater than 0. Why? Because now we suppose Cauchy definition is valid. So it's satisfied, right? And it means that for arbitrary epsilon greater than 0, there exists delta greater than 0. So once we choose this delta greater than 0, then I can take that delta from the Cauchy definition for substituting to the limit of this sequence. So here I'll put delta. So look, for arbitrary epsilon, we choose delta greater than 0. And from that delta, for that delta, we can find natural n such that for all n greater than capital N, we have the following inequality. Moreover, xn not equals to p, hence I can insert here inequality that xn minus p is also greater than 0. Now look. Then, for those values of xn, right, with n greater than capital N, we have precisely this chain, this supposition. So xn is in D, because all members of our sequence were in D, and 0 less than xn minus p less than delta. So it means those values of xn can be substituted here, hence by Cauchy definition, we have the inequality for the values f of xn minus L less than epsilon. So now what I need, look, for arbitrary epsilon greater than 0, somehow using this delta, but now we may forget about delta, for arbitrary epsilon greater than 0, we found natural number capital N such that for all n greater than capital N, we have f of xn minus L less than epsilon. Look at the parts which are underlined twice. Altogether, they are equivalent to this limit. Limit of f of xn equals to L. Look, for arbitrary epsilon greater than 0, there exists natural n such that for all n greater than capital N, f of xn minus L less than epsilon. So this part is done. Okay. Now from Heine to Cauchy. So Heine to Cauchy. And we'll do it by contradiction. By contradiction. So what it means by contradiction? It means that we suppose that Heine definition is satisfied, so this part is satisfied for arbitrary sequence such that and so on there exists the limit. We suppose this is satisfied. And by contradiction, we suppose the Cauchy definition is not satisfied. If it is not satisfied, it means that there exists epsilon greater than 0, so opposite, such that for arbitrary delta greater than 0, there exists x in D 0 less than modulo x minus p less than delta, and f of x minus L greater or equal epsilon. Let me denote it by epsilon naught, that is a fixed epsilon positive. Right? Okay. Now here it is written arbitrary delta greater than 0, right? So let us choose arbitrary delta as we want. Let's start delta equals to 1, then delta equals to 1/2, then delta equals to 1/3, and so on. Delta equals to 1 over n, and so on. All those values are positive, and okay, look, delta equals to 1, there exists x, and I'll denote this x, let's call it x1. There exists x1 in D, right? And that inequality is valid. So here it is written, there exists x, and I'll denote this x which exists for that value of delta by x1. And simultaneously, the inequality f of x1 minus L greater or equal to epsilon naught is satisfied. For delta equals to 1/2, again there exists x. I'll denote it by x2, and it satisfies that chain of inequalities. F of x2 minus L greater or equal epsilon naught. For 1 over 3, again there exists a value which satisfies now this inequality. And so on. So it means that we have constructed a sequence xn which satisfies simultaneously those two inequalities. Now look at this. So what can we deduce as n tends to infinity? The right hand side and the left hand side, both sequences, tend to 0. Hence, two policemen theorem guarantees that the middle part tends to 0 as well. So it means the limit of xn equals to p. Moreover, look, xn is in D and xn not equals to p, because for every n we have greater than 0 here. Then, by Heine definition, we should deduce, look, we have a sequence xn in D such that xn not equals to p and the limit of xn equals to p. Hence, by the Heine definition, we have limit of f of xn equals to L. But then, from those two facts, from this limit and this inequality, what we deduce? Substitute the limit. Okay, I may write so now we have modulo A minus L greater or equal than epsilon naught, and that's impossible because here we have 0 and epsilon naught is a positive number, and that's impossible. That is a contradiction. Okay. Maybe, a couple of corollaries. The first corollary says that corollary 1 the limit of a function if exists is unique. Why? Because if we would have two limits, then according to the Heine definition, it would mean two limits of this sequence, and that's impossible. Corollary 2 allows to use the negation of the Heine definition to prove the absence of a limit. So limit x tends to p f of x is not equals to L is equivalent to what? That there exists a sequence xn in the set D. Recall f is from D to R, P is a limit point of D. This is supposed, of course. Yeah. And xn not equals to P, and the limit of xn equals to P, but the limit of the sequence f of xn is not equal to L. So it means either it doesn't exist or it exists but is different from L. That is the negation of Heine definition. And in fact, we may even to make it look, this corollary says when the limit is not equal to a fixed number L, right? And corollary 3 says that, again, on the same suppositions, f from D to R, P is a limit point of D, and there exists no limit as x tends to P f of x, if and only if there exists two sequences, x and 1, and x and 2. D. Both not equals to P for arbitrary and natural, and both limits of both sequences are equal to P, but limits of the sequences f of x and 1 and f of x and 2 are different. Why? because if we suppose if this is L1, might be the limit equals to L1, but not because of the second sequence, and vice versa. So now an example 3, right? Example 3. The Dirichlet function. Dirichlet. Example 3. Dirichlet function. Which is defined as follows. So f of x, is it f? Okay. It's 1 if x is rational, 0 if x is irrational, not rational. That is the function. So for arbitrary p in R, there exists no limit as x tends to p f of x. Why? Because take arbitrary p, let's say p rational. Take arbitrary p rational, right? Then put x and 1 equals to p plus 1 over n. Then this is rational. It doesn't equal to p. The limit x and 1 equals to p, but the limit of the values look, all x and 1 are rational, hence the values of the function are equals to 1, and the limit of the constant sequence is 1. And if we'll take x and 2 equals to, let's say, p plus square root of 2 over n, then it is irrational. X and 2 not equals to p. The limit of x and 2 is p, but the limit of the values of x and 2 for arbitrary irrational number is 0. So you see they are not equal, and by corollary 2, no limit at a rational point. And for irrational, so now take arbitrary irrational point. Again, we can take x and 1 the same as before, p plus 1 over n. Now this will be irrational for sure. This is not rational, hence the sum is not rational as well. Then 1 not equals to p. The limit as n tends to infinity x and 1 equals to p, and the limit of the values equals to 0 now. And for x and 2. Okay, we want to have a rational number, right? So let's say rational number, right? So let's say 10 to the power n times x and 2, right? Take integer part. So it means integer part, and take 10 to the power minus n here. That is for sure a rational number. And again, all of them are not equals to p, since p is irrational. Oh, sorry, here p. So p here. P here. Yeah. And the limit of x and 2 is p. Why? Because look what we did. If we multiply p by 10 to the power n, it means we moved a point in the decimal representation for p in n digits to the right. And then we take integer part. It means we forget about everything after that point.